Hello honors physics students, let's go ahead and get started in our problem set with problem number 40. So go ahead and read it, do all of part A all on your own, pause the video as you do so, and come back to see how I do it. Okay, so after doing a bunch of these problems, I hope you really figured out how we approach them, that everything is rather abstract, it's tough to visualize these tiny charges, and so drawing a picture, a diagram, is the best way you have of visualizing what's going on. So hopefully that's what you did. I hope that's what you did. And so hopefully you set up a coordinate plane, you put charges 1 and 2 there so you can see where they are and how they relate to the origin and how to calculate the field at the origin. I know from experience some students don't quite read the ordered pairs as carefully as they should. Notice that the x-coordinate is 0 in both of them, which means that both of these charges are lying on the y-axis, and so maybe at this point you may want to adjust your picture. We want to try to draw it somewhat to scale so we can visualize it a little bit better, and so we know that charge 1 is 0.5 meters above the origin, and charge 2 is 0.7 meters below, and so it should look something like this, where charge 1 is a little bit farther, charge 2 is a little bit farther away from the origin, as shown here. I didn't exactly measure, but 0.7 certainly should be shown as larger than 0.5. And here Q1 is negative and Q2 is positive, so we can visualize that. Okay, great. So we want to find the net electric field at the origin, so hopefully we recognize we're looking at point charges, so we know we're going to be dealing with the equation E equals KQ over R squared, but let's remind ourselves which charge is it that goes in there. Well, what's really happening here is both charges contribute, and the key word here is that it says the net electric field. So what sort of problem is this? I hope you didn't just say it's an electric field problem. It's more than that. It's a superposition problem. Each charge has its own field. We calculate the contributions separately and then put them together to get the net field. So for example, E1 is there from charge 1. And so if it's bothering you that we're using capital Q for source charges here and here we're using lowercase q because that's what's in the problem, hey, if you want to call this capital Q, you can do that. All right? And by a similar token, E2 is a field produced by charge 2. So we want to call this capital Q2. So we maintain our symbols here, that capital Q is the source charge. In the end, you should have the flexibility, you should be able to see it doesn't really matter whether it's lowercase q or capital Q, but if it helps you, if that's what you need, go ahead and do that. Okay, so at this point, if you didn't get this far, go ahead and do your calculations and come back to see if you can get the right answer. Just some checkpoints along the way. For E1, we should be getting 201 newtons per coulomb. For E2, we should be getting 144 newtons per coulomb. Remember, these only give the magnitude. If you got a negative, if you got a negative for this one, you're doing it wrong because you shouldn't be getting a negative. You should be putting absolute value here, and even though charge 1 is negative, you should be just getting a magnitude. How do we know the direction? Well, we know our rules, and always in the back of our head, we're thinking about rule 1. Right? So we imagine our positive test charge at the origin. And why are we putting the origin? It's because that's what the problem says. We're finding the field at the origin. This charge creates a field at the origin. This charge creates a field at the origin. How do you know the direction of the field? We imagine our positive test charge. Don't actually draw it. Just imagine it there and see which way would this feel a force from each charge. Right? This is how we originally started our ideas of fields. Just look at one charge, then the other, and then put them together. So from charge 1, which way does our test charge feel a force? Well, our test charge is positive. It is negative. It certainly will feel a force upwards, and so the field at that point from charge 1 is up towards itself. Right? Okay, what about from charge 2? Well, our test charge would be repelled away from it, so that field is also pointing up. And so here we see these fields reinforce each other. Right? So here's the field, the 144 newtons per coulomb. I've drawn the 201 newtons per coulomb larger because, it is the net field is the combination. Or you can establish a positive direction and add them as vectors. Either way you do it, you should have no problem getting 345 newtons per coulomb in the upwards direction. Now, here's what's key. Is there a charge there? Well, in part A, no. We just have the field there, right? So if we want to make sure we're really understanding this, that's why we don't draw the charge. This field, this 345 newtons per coulomb in the upwards direction, is there at this location, whether or not a charge is there to experience it. That's why we never draw the test charge, because it's just imaginary. We just use it to imagine which way the direction of the field is and what a charge would do if placed there. Okay? So we want to make sure we're clear. The field exists because of charge 1 and charge 2 at this location, even if the test charge is not there. Now we get to part B. Okay, now we actually do put a charge there, and it happens to be positive, so here we're going to relabel these as lowercase q, and lowercase q3, and so go ahead and pause the video, try all part B on your own, then come back to see how I solve. Alright, there's a bunch of ways to do this. There's the longer ways and the shorter way. I'm going to go through all of it. Okay, so again, hopefully you notice everything here is point charges, so yes, we are justified in using Coulomb's law. This is a great time to use Coulomb's law, F equals K, big Q, little q over R squared, and again, it doesn't really matter what you're calling big Q or little q as long as you're only pairing up 2 charges at a time. And remember, we can only use this for point charges. So we have three pairs. We have the force of 1 on 3, the force of 2 on 3, and the force of 1 on 2. Do we do all three of these? Let's read the problem carefully. We want to find the magnitude direction of the force it would experience, it being charge 3. And so charge 1 and 2, while they do exert forces on each other, we don't care. We don't care about that. We're not right now not looking at those charges, right? This goes back to when we first were talking about fields. Do charge 1 and charge 2 exert forces? Yes, they do. Is that what we care about? No, it is not. Because the problem asks for the force on Q3. So we don't care what charges 1 and 2 do to each other. So all we want to know is the force that charge 1 exerts on 3, the force that charge 2 exerts on 3. And so you can just use Coulomb's law, find the individual forces, add them as vectors. That's great. Alternatively, hopefully you realize that we've already done some of the work. Here is kq over r squared, and we've already calculated for both E1 and E2. This lowercase q, that's the other charge in the interaction, that's the Q3 here. So really, we just do F equals QE twice. The charge experienced in the force is Q3 because of charge 1's field. We do it a second time. Q3 is the one experiencing the force from charge 2's field. And we've calculated both those things. So we can sort of bypass the step of putting all these numbers in because we've already done the work. And that's really what I'm trying to show you here. So we've already done kq over r squared. Why do it again? Right? Just multiply the results by q. You find the individual forces, put them together as vectors. So this is like superposition of forces. As opposed to over here, we're just superposition of fields. But wait a second. Why are we doing the individual fields? We know that these two fields contribute, and we found the net field as 345 newtons per coulomb. So why don't we just use that? Let's not worry about any of this stuff. We already found the net field. Let's just do F equals QE once using the net field. This is the best way to do it. And this is really what I'm trying to get you to do, is look for these shortcuts. Things, why reinvent the wheel? Why do the hard work if we've already done it? You'll get the same answer, or very similar answers, but why? Right? Might as well just make your life easy. Alright, so make sure you're putting the charge in. Here's the 9.8 microcoulombs. And something I forgot to mention before, just make sure, of course, we're converting. Right? If you're getting the values of these completely off, you probably forgot to convert, or maybe converting correctly. These are nanocoulombs. Nano numbers 10 to the negative 9th. It's microcoulombs. That's 10 to the negative 6th. That's Q3 there, right? So 9.8 times 10 to the negative 6 coulombs times the net field there, and you'll get the magnitude as given like so. How do you know the direction? It's rule 1, right? It happens to be a positive charge. Positive charges feel force in the same direction of the field. So if the field is upwards, then the force on that charge is upwards as well. We're always thinking about rule number 1. It's the easiest way to think about it. All right, let's backtrack here to problem 33. All right, so go ahead and do all problem 33. Come back to see how I do it. Okay, this is real simple stuff. I mean, it should not have taken you very long. We're just using this equation, delta V equals W over Q. Now, I say it's real easy, we're using this equation, but still I know some students get a little confused because they say, wait a second, that's not the equation we have. We have delta V equals negative W sub E over Q. Well, what does W sub E stand for? That's work done by the field. What does the problem say? It says you are doing 12 joules of work. Well, you're not the field, which means you should not be using an equation that says negative work over charge. If you are, you're doing it wrong. And you still are not understanding the difference between the work done by the field and the work done by some external agents. You want to go back to our previous lesson where we went over that in detail, right? And in general, the work that you do is the opposite in sign of the work done by the field, so we just immediately replace this with just work per charge. And so we're moving from point A to point B, so it's VB minus VA, and the math is real simple here. We should get 12,000 volts. Simple. All right. Do a similar thing for part B. We're again doing delta V equals work over charge, so it's the field, or the potential difference between B and A, and we get the 12,000 volts again. Great. Of course, hopefully you notice something very interesting. What happened here? We got the exact same potential difference, even though it's a different situation. Why does that happen? Well, a couple ways to think about it. One is this, right? We took a charge that's twice as much as this one, and what happened to the work? It required twice the amount of work. So when you put those values in, it's twice the work for twice the charge. You can clearly see the twos cancel, and you get the exact same results as before. Hopefully this reminds you of something we've done before, right? Maybe think back. What did we do that was very similar to this? Well, it all had to do with what's creating the effect and what's experiencing the effect, right? The potential difference here is created. It's there. This charge, whether it's the 0.01 coulombs, the 0.002 coulombs, that's the moving charge. It's not affecting the potential difference. Just like a test charge doesn't affect a field, this moving charge has nothing to do with the potential difference. So you can see that clearly here. If it's double the charge, it just requires double the work to move it through the same potential difference. In a more visual way, let's draw a situation here. It says the uniform electric field, so let's draw some oppositely charged parallel plates, maybe like this. We'll draw the electric field pointing from positive and negative. The field lines are perfectly straight. They're parallel to each other. It's our ideal uniform electric field. Since we're moving this positive charge from point A to point B, and we're doing positive work to make that happen, let's say here is A, where it wants to be, and here's B, where it doesn't want to be. So clearly it's going to take positive work to force that positive charge there. In fact, we can even establish the potentials at each of these plates at B and A, based on the fact we know there's a 12,000 volt potential difference. Go ahead and do that on your own. If we follow our convention, we know that the positive plate here is like the top of the mountain, or negative plate is like the bottom of the mountain, and we can always call the negative plate the lowest potential, so we can call that the 0 volts, which means this must be at 12,000 volts. And does that change when we change what charge is? Well, have we even drawn a charge here? No. And that's really what I'm trying to get at here. What creates the potential difference? The plates. The plates create the potential difference whether or not there's a charge there to experience it. This goes right back to how we first introduced this idea with the hiking analogy, right? If we cancel the trip, if we never drag that cooler food to the top of the mountain, does the mountain disappear? No. What's the mountain? Well, that's the plates. The plates create this potential difference. Because of their charge, because of their separation here, they create a 12,000 volt potential difference. And if a charge moves around between them, it'll take work one way or the other to move it one way or the other. But no matter what, this difference here is 12,000 volts because it just exists. Another way to think about it is that shortcut equation, that delta V equals E delta D, which remember we got here by canceling out the moving charge, really highlighting the potential difference has nothing to do with this moving charge. That's why it dropped out here. It's just created by the plates, by their charge, by the field they produce, and how far apart those plates happen to be.